Good morning, and welcome to the fourth ATCO SpaceLab Speaker Series of 2025. My name is Kelsey Stephen, and I am a member of ATCO's transformation team, and I will be your moderator today. While today we're gathered virtually, I ask that you join me to reflect on the meaning of place to recognize the significance of the various traditional, ancestral, and unceded lands on which we're located. With gratitude and reciprocity, I acknowledge that I live and work in Treaty 7, the traditional territories of the Niitsitapi of the Blackfoot Confederacy, comprised of the Siksika, Kainai, and Piikani nations, the Tsuut'ina Nation, and the Ithaka-Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. This land is also home to the Northwest Métis and to the Otipemisiwak Métis government, Nose Hill Métis District 5, and Elbow Métis District 6. Today's lecture is a one-way video and audio format. Please ask questions by using the Q&A button at the top of your screen, and we will get to these at the end of the lecture. I will now hand it over to my colleague, Andrea Kleiber-Langen, to introduce today's speaker.
Thank you, Kelsey. Welcome, everyone. Thank you so much for being here. Today, we are joined by Dr. Shankar C. Venkataramani, an accomplished professor of mathematics at the University of Arizona. Professor Venkataramani received his PhD from the University of Maryland. His research spans partial differential equations, differential geometry, and statistical physics, with applications in material science and biomechanics. His work has been recognized with the National Science Foundation's Career Award, as well as Sloan and Simons Fellowships. Today, Professor Venkataramani will share his expertise on the interplay of geometry and elasticity in biological systems. We will explore examples such as the ruffled edges of lettuce leaves, the undulating motion of sea slugs, and the intricate optical structures responsible for coloration in butterflies. In examining these examples, we uncover how curvature, elasticity, and material properties shape functions across diverse organisms. These insights not only enhance our understanding of natural design, but also inspire potential applications in biomimetic engineering and materials science. We look forward to learning from you, Professor. Please go ahead when you are ready.
Thanks for the introduction. My name is Shankar Venkataramani, and I'm a professor in mathematics here at the University of Arizona. And I have a couple of videos here to illustrate the kinds of things I'll be talking about. On the right, we have a marine flatworm, and you can see the way in which it swims. It's very smooth and undulating and very unlike, say, walking or even how other fish swim. On the left, we have an award-winning short film that was made by this filmmaker who had a friend that works with butterflies. And she made a movie about the nanostructure of the butterfly wings and the fascinating ways in which these structures actually interact with light. And so what we see is not often because a butterfly has a pigment of a certain color, but really it's because of the way in which these structures, which are on the scale of 100th of a human hair, influence light waves and especially ultraviolet waves. Okay, so these are some of the things I'm hoping to get to, but it's going to be a kind of twisty journey that gets us from math to these particular biological systems at the end. Okay, so here is by way of motivation. It's very clear to us whether something is natural or something is made artificially. And one thing that we see in natural structures is there are very few straight lines. And the structures are often ruffled, smooth, curved, undulating, and not one that have corners or edges or folds, but really it's much more likely that we see. I mean, it is not much more likely. This shape is prevalent in nature, and this was initially kind of the motivation for why I started looking at some of these questions. So why is it that some shapes occur all the time in nature, but not so much in engineered structures. And what is it about these shapes that nature prefers them? So a study of this leads naturally to a question of geometry. How do we understand these things geometrically? And the more specifically, the question we're interested in is the kinds of buckling behavior we see in geometry. So we don't see flat objects. We see objects that have a structure on top of this flat state that of buckles. And sometimes these buckles have further buckles, and those have further buckles, and so on. So you get generations of this buckling. So why is this something that we see in nature? There are teleological explanations of the type that nature wants to do this, and that's why it does it for various purposes, maybe for transporting nutrients or maybe for growth. So, but even if nature sort of wants to do a certain thing, there's also the mechanical question of how does it do this thing. So let's say it's established that for some purpose it's good to have this kind of shape. How is it that a biological organism grows or develops to achieve this shape? Because it still has to satisfy the rules of physics and mechanics. So what we are looking at, in a way, is not maybe an explanation from the point of view of, say, natural selection, saying there's pressure, natural selection pressures that prefer this kind of shape, but more pragmatically, what kind of mechanical structures or mechanical properties will lead to these kinds of shapes. So that's the framework in which I'm going to look at these questions. So what is geometry? And this is what the dictionary says. It's a branch that's concerned with relations of points, lines, surfaces, solids, and higher dimensional analogs. The first thing that we learn as people living in a three-dimensional world is there are different kinds of geometries. So there's the geometry, for example, that an ant walking on a surface would see. It does not need to know about the fact that the surface is in 3 dimensions. It walks along the surface. In a way, this is like us on the planet Earth. For lots of our history, we couldn't get off the surface. So all that mattered to us was the relation between different points on the surface, what is north of something else, or if you walk north 100 miles and then east 30 miles, you get to a different place. So this kind of relations among points within the surface is what's called as intrinsic geometry. And I like to think of it as the geometry that an ant that does not have conception of anything off the surface, that's what it would see. But we can also conceive of this object in 3 dimensions, and the difference or the extra ingredient that we get by looking at things in 3 dimensions is information that's encoded in what's called the normal. So what's the normal? So here is, if you want a garden tamper, you can take a surface and imagine putting a tamper at every point, or walking around and then sticking this tamper on the surface. Then the handle is going to point in some direction now in space. It's not in the surface anymore, it's perpendicular to the surface. So this extra information, which is not available to an ant, is what constitutes the extrinsic geometry of a surface. So if you take a sheet of paper and you roll it up into a cylinder, for example, you're not changing the intrinsic geometry in that an ant on the sheet of paper would not really know that you did anything, but you are changing its extrinsic geometry because how the object lives in 3 dimensions is now different. And that's what this is supposed to represent. So on the left is maybe an initial representation of a material object. We are doing something to it, and so what we get to on the top on the right is how it looks in 3 dimensions, and that has some deformation within the surface that's intrinsic, but it also has this extra information about what is the normal or the perpendicular to the surface at every point. And you can think of that as a point that lives on a sphere. So you have a handle of a fixed length, just changing direction. So that gives you a sphere. So there are now 2 geometries to consider, the intrinsic and the extrinsic geometry. And so where does mechanics come into this problem of geometry? It comes in the following idea. So physics suggests that changing intrinsic geometry, right? So that would be like stretching this band, because that is something that would be visible just within the band. You've changed distances within the band. That's changing the intrinsic geometry. That's pretty hard. But changing the extrinsic geometry is just like bending the band without stretching it at all. And that's pretty easy. Okay? So these systems, which are thin and elastic, there's this nice connection between the geometry and the physics or the energetics of the system, in that it's very hard to change the intrinsic geometry, but it's very easy to change the extrinsic geometry. And just this simple idea about thinking in terms of the extrinsic and intrinsic geometry actually gives a lot of insight into understanding how these objects behave. So this is just recapitulating what I just said, that bending is easy and stretching is hard. So there are 2 energy scales in the problem. And now here is the extra ingredient that makes these problems mathematically interesting, which is, although bending is easy and stretching is hard, bending and stretching are dependent in a way. Okay? And so what do I mean by this? So here is an experiment on my tabletop. I just took a sheet of paper and 3 stacks of quarters, and you put them all on an edge, and you see that the paper likes to bend over the edge of the table. Now, if I did the same experiment where I put 2 stacks under the paper and 1 stack on top of the paper, what you see is something very different. You see that the sheet doesn't want to bend over the edge of the table anymore. So why is this? And the answer to this question actually connects with the fact that if the sheet now tries to bend over the edge of the table, it will have to stretch. So the fact that you bent it already in one direction makes it rigid because it does not like to stretch, and any extra bending will cause stretching. So 2 independent curvatures cause stretching, and that's kind of the idea behind what this suggests. So in fact, this is a very fundamental theorem in differential geometry. This goes back to the work of Gauss, who was a preeminent mathematician of the 18th century. And he called it his egregious, or really that means surprising and remarkable theorem, which is the following fact. So given any surface, we can define intrinsically a notion of curvature. That is, you don't need to get off the surface. And the intrinsic notion of curvature has to do with what happens to triangles on, for example, on the surface. And so here I've drawn triangles on a saddle, on a cylinder, and on a sphere. Now, on a saddle, so these lines that connect points are really the lines that have the shortest length between these 2 points. So they are the analogs of straight lines. Now, on a cylinder, you can think about unrolling the cylinder. It just becomes a flat sheet of paper. A triangle in a flat sheet of paper, this is what we learned from high school geometry. The angles have to add up to exactly 180 degrees. Now, on a saddle, because of the way the saddle is shaped, it turns out that the triangles are a little bit skinnier than what they would be on a cylinder. So the angles add up to something less than 180 degrees. And on a sphere, this is, of course, the idea that's in this usual riddle about, you're following a bear, you walk 100 miles south and 100 miles east and 100 miles north, and you're back where you started. What is the color of the bear? And you're supposed to recognize that you're close to the North Pole because that's the only place where you can make 3 right turns and end up back at the same place. And that you cannot do on a plane. So this is on a sphere, the triangles are fatter than the triangles would be on a plane. And on a saddle, they're thinner than they would be on a plane. And you can actually measure the angle defect, which is how much are these angles adding up to be more than or less than 180 degrees. And that gives you a definition of a quantity called the curvature. Okay? So it's positive for a sphere, is negative for a saddle. That's purely intrinsic, right? That like the story of, following a bear, you just were on the surface and you could measure this quantity. You could also think about this extrinsically. And extrinsically, you can, put a normal at different points, and you can look at how the normal is curving. And then that gives you 2 curvatures in independent directions, and that gives you extrinsic definitions of curvature. And so Gauss's theorem, the remarkable theorem, says that the intrinsic curvature, which you measure using these angles, is the product of the extrinsic curvatures. So there's a balance. If one extrinsic curvature goes down, the other has to go up so that the product stays fixed. That's the math which explains a lot of the physics and the biology that we're going to see. So there are various consequences of this. So for example, this is how we eat pizza, right? It's the same as the tabletop experiment. You fold pizza a little bit in one direction and then it becomes rigid in the other direction. Whereas if you just try to lift a pizza up by holding onto the crust, it's going to drop all of its toppings. And so the blue and the pink lines here are the lines which measure curvature. In this case, the product has to be 0, which means if you put a little curvature along the pink line, it automatically forces that the blue line has to be straight because the product has to be 0. So that's one manifestation of this theorem. This is also relevant to the problem of how I actually got into this subject in the first place, which was looking at how paper crumples. And now you might wonder, what's such a big deal about paper crumpling? Of course, it has to crumple. So as an engineer, here is kind of the question. So here is the idealized experiment that crumples. You take a sheet, you put it on inside a large sphere, you shrink the sphere down uniformly, you're going to end up with crumpling the sheet inside. Now, you're not doing anything non-uniform. You're forcing the system uniformly on a large scale. So if you think about crumpling, it's on the scale of your hands, which is a few centimeters. But the kinds of responses that you get are on a much, much smaller scale and extremely non-uniform. So how is it that a uniform forcing of some large system ends up giving you a very non-uniform and much finer scaled response in your material? And so when we started looking at this problem, we thought this might be maybe an analog of really a very important kind of holy grail problem in physics, that of turbulence. And so in turbulence, you stir your system up on some large scale, and then you get this very, very small scale complex behavior. And that's exactly what we're seeing. Of course, here the answer is that because of this theorem that says that if you bend in one direction, you have to be flat in the other, that tells you that you cannot put it inside a small inner sphere because that will need you to bend in both ways. Now, if you bend uniformly both ways, you're going to stretch everywhere in the sheet, and that costs a lot of energy. So what the sheet ends up doing is it tries to minimize the set on which it needs to stretch, And that's exactly what these creases and these points are. That's where the sheet has to stretch a little bit, but it's minimizing the set on which it stretches, and that's how we get these shapes. So that's crumpled plate. Here are examples that are closer to what I'm trying to get to, which is what happens now if we take a sphere and try to make a representation of it in the plane. Now, because the sphere and the plane have different intrinsic geometries, we have to change the intrinsic geometry. What does that mean? That means we have to deform, or we have to do something to the surface. There's no way of making a map of a globe on a flat sheet of paper that does not distort either the areas or the lengths or the angles. We have to distort something. And this is, of course, relevant because, Greenland, for here, example, looks much bigger than Africa or a comparable, whereas in reality, it's like a fraction, like a 20th or even smaller, the size of Africa is. And that has real consequences for how people think about their place on the globe and about sort of how important or big certain things are compared to something else. So the fact is the globe, a sphere, cannot be represented on a plane without distortion. That's what happens with a sphere. Now, we saw earlier that a sphere had positive curvature. What about an object with negative curvature? And that would be like a saddle, or, like I like to say, an anti-sphere. Now, it turns out nature really likes the anti-sphere for its geometry. And why is that? So, a universal process in biological organisms or natural things is growth. And some organisms grow all their lives. Some organisms, grow in different phases and reach some kind of maturity, but nonetheless, there's growth. And so imagine this is a mathematical model of a flower. You have a flower that's growing. And what happens as it grows? As it grows, each layer of cells produces the next layer of cells. Now, if each cell produces just one daughter, you're going to get a cylinder. But that's not what nature does. Nature grows in that each parent cell produces two or some number more than one on average of daughters. In that case, what you will get is not a cylinder because each new layer is bigger by a factor than the previous layer. So that's kind of what this is. So if you go ahead and look at the cells in it, you will see that on average, some cells might produce one daughter, but some will produce two. So there's going to be on average a growth. So here is an example. That's why is this kind of an anti-sphere? Going back one slide, the sphere has a property that you start from the equator, and as you go toward the pole, your circles are getting smaller and smaller. Whereas here, if you think about this neck as the equator, as you go out, the circles are getting bigger and bigger. So this is the kind of object that one should expect in nature from just the dynamics of how things grow. So this anti-sphere is then an example of hyperbolic geometry. So here's a way of thinking about what is hyperbolic geometry. And this is done with like bread, but you can think about each of these as a cell. And in a way, the number of cells are increasing rapidly as you get further away from where you start. You should think about all of these pieces of bread as being the same size. And then if you take such an object and try to represent it on a flat plane, it's clear that you have to make the representation of these objects smaller and smaller as you get away from where you start, just because there's so many of them. And so it's the opposite problem of Africa and Greenland. Here, things near the equator seem to be bigger than they are relative to things that are further away from the equator. Okay, so that's the opposite of a sphere, and that's the natural thing that's the geometry that nature prefers. So here is an example of such an object, and so this is a woodcut by Escher, and it's a representation of this kind of hyperbolic geometry or the antisphere, a map of it, as you will. So on the left, all the fishes, you can think of them as countries that are exactly the same size. And then from the fact that they live on this hyperbolic plane, which is the counterpart of the sphere, you see that when you draw it on a plane, you have to make the countries that are further away from the center look smaller, although in reality they're all the same size. And the woodcut on the right has angels and devils. All the angels are really the same size, and all the devils are also really the same size. But again, they look smaller and smaller as you get further up. Okay? So that's a representation of this thing in the plane. The question we are interested in is what is the actual shape of this thing in 3 dimensions? Right? We don't just care about making a map of it. We care about the actual geometry of this object. Okay? So here is another remarkable fact. And a way to paraphrase this question is, let's say you have a Pringle, right? That's a potato chip that's shaped like a saddle, and you want to make the biggest Pringle in the world. How big can you get? So what surprisingly, it turns out the answer is that there is a limit. And so this is a theorem that goes back to Hilbert and Efimov that says that if you have, and so there's some technical condition, a 2 times differentiable surface that has constant negative curvature, it has a limitation on how big it can be. And the problem is, for example, illustrated on the left, is that as you make this bigger, you have this horn-shaped object, which you can think of as a growing flower. Now the flower is growing. At some point, the rim of the flower becomes 2 pi times the distance from the axis. That's the circumference. Now to go beyond this point, the rim has to be even longer. And there's just no way in 3 dimensions in a plane to make a circle that's bigger than 2 pi r. So what do you do? And that's a problem, and that's exactly what this theorem encapsulates. So this would suggest that natural things, if they grow, they are bound to run into a limit on how big they can be. But of course, nature doesn't like to be constrained. It turns out nature finds a way around this theorem. So here's how corals and crochet. So here are examples of these objects, and you can see you can also make this by crochet. And the idea is you add an extra knot every layer in a way that the thing grows by a factor each time. And here it's kind of reaching the limit of what it can do, staying saddle shaped. But you can keep crocheting, and what it does is it then forms these extra buckles. So it goes from being simple saddle to being something more complicated and to more complicated and so on. And that's exactly what nature does as well. And you can actually have a crossover between these. You can make crochet that look like corals. There's a very nice art and science project, a traveling exhibition where people from all over the world have contributed to this crochet coral reef by making crochet that looks like these corals. Okay. So what is the mathematical and the elastic basis for this? That's my question. So all of this is work that was done with my students. So John, Toby, and Ken have now graduated and moved on to other things. Ari is a current graduate student who's working on some of the dynamics of these surfaces. So we're going to talk a little bit more about these saddle surfaces and what they look like and what can we say about them. And so this is a model of a saddle. This is actually here in the math department at Arizona. We have a display case where I guess in the 1900s, there were these companies that would make these models of geometric objects and sell them to various universities. So we have a case full of surfaces of various types. And the thing to notice about the saddle is it's woven by strings that are all straight. Although the surface is curved, there are two sets of straight lines that live within the surface. That's not an accident. And in fact, Etsy sells these things. You can get your own hyperbolic surface, and you will see that the way it's made is by having two sets of straight lines. And so, this is in a way very interesting because we said that nature doesn't like straight lines. Engineering does very much like straight lines. But here is an object that's not flat, but can still be engineered because it does have these straight lines in it. And so how does one exploit this? Here's one way in which this is useful. So because these saddle surfaces can actually be made using families of straight lines, you can actually make roofs of this type, which are actually structurally quite good. You just have to use a bunch of cross beams in both directions, and that naturally makes a roof that's both aesthetic and good for, water from the rain, for example, will flow down quite easily, and so it's got nice properties. So it's also an interesting architectural element. So nature goes one beyond this, and what nature does is the following. So it is true that we can have surfaces made from these two families of straight lines. So what we can then do is cut such a surface along these straight lines and make a sector that's bounded by two straight lines. The surface itself is curved, but it has a boundary that has two straight lines. Now, mathematically, we can show that you can change, or you get to pick what the angle is between these straight lines. So there is an example where this angle is exactly 60 degrees. And if the angle is 60 degrees, then you can see immediately that by taking 6 copies of such a surface that's bounded by straight lines and with an angle of 60 degrees and patching them together, you can make a new surface that's saddle-like, but it's not quite a saddle. And why is it not a saddle? A saddle has sort of 2 ups and downs. This one has 3 ups and downs. So it's a monkey saddle, right? So the monkey has space to put its tail as well. This happens in nature. So here is a monkey flower, which is again one of these surfaces that is a saddle with this 3-fold symmetry. So for our purposes, what this is telling us is that you can make surfaces where you can add this extra buckle to it. And these surfaces are not 2 times differentiable, but they still look pretty smooth. Okay, so let's talk about what this means. So if you have a shape, and that's what this purple curve is, we say that it has a fold or a corner if the tangent lines on the 2 sides are different. So that's exactly what it means to say it's folding. Let's say you're traveling along this purple curve, you change direction at a point. Now there is a weaker kind of change of direction, and that's what is reflected in the curve on the right. So this would be if you're driving along a road that initially the road was veering to the right, and then at some point it starts veering to the left. So here the direction is not changing. What is changing is the curvature. You're curving one way on one side of this red point and curving the other red. So this object on the right is smoother than the object on the left. And in fact, this is exactly what happens. This is my neighborhood here in Tucson. And you can see that there are places, for example, at the intersection of Whittier and Longfellow here in the lower left, that it's a corner. To go from Longfellow to Whittier, you actually have to change your direction from going north-south to going east-west. But there are other places, for example, along these curved streets, where you can more gradually, you don't change the direction, but you change the curvature. So what's this got anything to do with what we're talking about? And so here is the connection. If you have a flat sheet, because of Gauss's theorem, it turns out to deform it, you have to put a fold or a corner in it. But if you have a hyperbolic sheet, you don't need to put a fold, you can put an inflection. Now, obviously, putting an inflection is much less damaging to the surface than putting in a fold. And so nature, in a way, one explanation for why you'd see these hyperbolic surfaces in nature is because it allows for this possibility of inflection. You might say, well, what's such a big deal about allowing the possibility of an inflection? And so here's the answer. Origami. Okay. So what is origami? You start with a flat square, and then you put some folds in it, and you end up with a shape. And again, there are some rules about what is flat foldable and what is not flat foldable, but there are there's lots of different potential shapes, all within this one square sheet of paper, because we get to pick our folds in different ways. And way of expressing this in a way is to say that if you have n folds, you can have exponentially large number of possible shapes. So there's a combinatorial complexity to the possible shapes of origami. And by using origami, you can actually design various kinds of surfaces. So all of these come from an initially flat square. And this is work of Mahadevan, who's a professor at Harvard. But so here is again a possible concept that NASA is playing with, which is to have a space telescope. A problem is that you have light from the sun or other sources that make it that you cannot view a distant object well. So you can have sort of a star shade. So by origami, you can pack it up into a little region, and then you can block off the sun, and then you can really study whatever else that you're trying to study. Okay, so that's the potential of origami. What we can do with hyperbolic surfaces is a version of hyperbolic origami, where instead of putting folds in the surface, we put these inflections or these undulations. And so that's the math we've been doing, trying to understand how do you design hyperbolic surfaces with undulations that can do particular kinds of things that you want it to do. And perhaps that's what nature is doing already. And so here is a few illustrations. I might go through this a little bit quickly, but the basic idea is illustrated by this figure A on the left, which is on these hyperbolic surfaces, which we said were ruled by families of straight lines. You have this possibility of surgery, where you can cut out a sector, that's what is in these green lines, and replace it locally by a monkey saddle. So you get sort of more families of straight lines at this point. And then you can do this recursively. So what you end up with is this kind of hierarchical multi-scale buckling that we see in nature. And again, all of this is done in a very smooth way. It does not change the intrinsic geometry. It's purely a bending kind of mechanism. And it also does the bending without putting in any sharp folds or corners. So it's a very smooth, very low energy way of deforming a surface, but to give you morphological complexity. So that's very much like what we see in natural systems. Yeah? And so this is sort of a mathematical representation of what we are doing. U and V for our underlying PDE are what are called characteristic directions. And we are changing the network of characteristics so that it's no longer combinatorially just the lattice in the plane, but it's a different kind of object. But nonetheless, all of this can be implemented mathematically, and then you end up with these kinds of surfaces that allow for extra buckles. So hyperbolic geometry is very, very flexible. Just like origami is flexible, hyperbolic geometry is flexible, but it's flexible in an even nicer way in that you can do all of these things with kind of soft deformations. And so we can also implement this to grow surfaces. And so that's work by Toby. You can see how these buckles come in as the surface gets larger. And then here is an example of a large surface that we can make this way. The colors may make it seem like, so the colors are a count of generations. The surface is actually pretty smooth looking, because the only thing it has are inflections and it has no corners, and you can make these things as large as you want. Okay, so a Pringle chip, which is like just a simple saddle, has a limit on its size, but a natural organism that exploits this ability to add extra buckles without any stretching is pretty much unlimited in how big it can grow. Okay. So now we are looking at sort of the mechanical properties of these things and also the dynamical properties. So let's say you do have a hyperbolic shape and you're willing to let this hyperbolic shape change. What can you see with it? And so on the left is a lab experiment. This is by Professor Eran Sharon, collaborator at the Hebrew University. On the right, we have a Spanish dancer. That's a kind of sea slug. And you can see that the way it gets around, it looks like it's being lazy and just swimming, doing its own thing, not with any particular purpose. But it is by these undulations, by these waves of curvature that it sends along its margins. And that's only possible because it does have a hyperbolic geometry itself. And then it kind of gets around doing this funny gait. So we've been thinking about this. Can we do this at least mathematically and build objects? So the objects on the right are what we might think of as hyperbolic soft robots. So the example on the top, you have a saddle surface. You can see that globally the shape of the surface is not changing, although in terms of the material is painted red, green, and yellow, the shape is moving relative to the material. So if this were a purely elastic material, then there's no energy cost to doing this because you're keeping the same shape, just different parts are up or down. But by doing this process, we can implement a global rotation of this object. You can see that the green sector is changing where it is in space, relative to, say, the table or the lab frame. So here is an example of having a zero energy budget of an object that can change its orientation. At the bottom is our crude attempt at mimicking what these marine flatworms or sea slugs are doing. And again, this is done using our framework of having these characteristic networks, and these networks are changing. So we can set up these curvature waves in our model organism, and it does this kind of undulating motion. So what Ari is working on right now is if we now couple such an object using fluid structure interaction with an fluid environment, will it swim? And what is its efficiency? What kind of gait will we see for its swimming, and how does that compare with these naturally occurring things? So there's already engineering applications for this, and so this is a video that was shared by some people I know at a small company in Brooklyn. They're using these kinds of undulating motions to possibly extract energy or build man-made materials that exploit these kinds of hyperbolic geometries to various ends. So that was kind of the first part of my talk. I realize I only have a short amount of time, so I'm going to just maybe a little bit superficially, but at least tell you what the main ideas are in our work on butterflies. So this is a different system. Again, we get these kinds of hierarchical multi-scale buckling, but here the geometry is a little bit different, and it's not really based so much on hyperbolic geometry as much as having materials with a contrast in material properties. So let me set the stage for what we are thinking about. So this is a butterfly wing. And on a butterfly wing, if you look at a microscope, you'll see that there are these scale cells. These are things that look like fish scales on the magnified image. And within the scale cell, you have, again, another layer of buckling on a length scale that's comparable to, say, the wavelength of visible or sometimes even ultraviolet light. So these structures are then photonic materials. They can interact with visible light, and they serve many purposes. So, they give you the butterfly, coloration. They're super hydrophobic, they don't get wet. They can give transparency in certain wavelengths. They appear dark to us, but actually they appear pretty vivid in ultraviolet just because we can't see ultraviolet. And so they're useful also for things like thermoregulation. And depending on the scale at which you have these buckles, they can also interfere with things like how bats use sonar for echolocating these things. It allows them to it's like a stealth. What's the right word? Anyway, so it's something that inhibits reflection of sound waves, and so these structures can occur even among butterflies and moths on various scales, and they actually can serve lots of purposes. So what is kind of the model? I'm going to. Our models are simple. It's that these are bilayer or multi-layer materials where the layers have different elastic properties. So a way to think about this is, let's say you have a soft foam, you stretch some harder or stiffer rubber, and you glue it on the soft foam and you let it go. And so the skin will want to shrink back down, but the foam underneath, will resist this a little bit. So the foam is going to deform in a way to form these kinds of buckles. And this can happen on the cells, this can happen on the cuticle, and this can give you different kinds of structures. And so the images here are really numerical simulations. And from a model, we can get things which look very much like the image on the right. So this is the second order decoration one sees on the first order structure, which is the thing we see on the left. So this is work. And so why might we care about this? If we can understand the mechanical basis by which butterflies solve this problem of making a photonic material, then perhaps we can also do this synthetically, by engineering materials that automatically self-assemble into similar structures, and that then has lots of applications, including here is an example of maybe building better kinds of solar cells. So that's a quick overview of the kinds of things that I'm thinking about. And so what next? Yeah, and the point I want to leave you with is why I like this kind of work, and I like it precisely because it doesn't fit into sort of one box. It really cuts across many areas of math, but also of physics and biology and engineering. And it gives me the opportunity to really talk to people from a variety of backgrounds and disciplines, and learn from them and learn about how other people think about these questions, and if there's some useful interaction between how maybe as a mathematician or an as a mechanician, I might think about these things to how other people think about these things. So this word cloud is just an illustration of all the various concepts and topics that are really relevant to some of the things that I've talked about today. So yeah, thank you so much for your attention. And this research wouldn't have been possible without my wonderful collaborators and my students, and also generous support from various funding sources, including the National Science Foundation, the Simons Foundation, and the Binational Science Foundation. So thank you very much.
Thank you so much for the wonderful lecture. You can stop sharing your screen now if you'd like. For everyone who's watching online, feel free to put your questions in the Q&A box at the top of your screen, and I'll read these questions out to the professor, and we'll get some answers for you. To get us started, I had a question. I'm really curious to know maybe some other applications. I know you talked about solar cells there at the end, and you talked about some soft robotics. But yeah, could you share some more examples of where your research could be applied?
That's a great question. And so some of the things that I'm thinking about are not necessarily even soft robotics, but the thinking in terms of the characteristic networks for those hyperbolic sheets actually allows us to design even rigid mechanical elements that can have those properties. So even perhaps easier than soft robotics would be to actually make mechanisms that are hard and that can move in prescribed ways, exploiting some of the extra freedom that we get from hyperbolic geometry. And so this is something that I'm thinking about because it seems to me sort of more accessible way of controlling these geometries that maybe people haven't thought about as much. And so that's one direction. With the butterflies, I think there's lots of potential for various things. One could think about doing this on different scales. You know, so for sonar, for avoiding sonar, and so on, for applications of that type, but also for self-organization. So if we can design just elastic materials or metamaterials that have interesting properties. For example, one of the key aspects to analysis of the butterfly wings is that the lower, softer material, usually in living systems, it has a lot of water in it. And water is very, very incompressible. So although it can deform, you cannot compress it. So this gives an extra facet to consider in how you do the analysis of these objects. So we could scale that up and look at structures that come from interaction between objects that deform in some ways but are constrained in other ways. And that was also one of the themes of the work on hyperbolic geometry, in that this was based on deforming sort of the extrinsic geometry, but keeping the intrinsic geometry fixed. So these kinds of constrained deformation problems, again, they haven't been investigated very much just from the mathematical perspective, but also in terms of how one might apply them. So I don't have, I guess, particular things that they might apply to, but just the fact that there's this entire avenue of looking at engineering problems in a different way, I think is fruitful, and things might come out of it. That may be an answer to the question.
Great. Thank you so much for that wonderful answer. We have a couple more questions coming in now. Our first question is from Syed, who asks, science fiction is influenced and inspired by real science, but what is your opinion or take on how sci-fi can inspire real life? And also, what is your favorite sci-fi concept?
There's so many. It's kind of hard to. Yeah, no, I agree that sci-fi is inspired by science, and it can also go the other way, as we are seeing, many of the moral and ethical questions that sci-fi explores before the science becomes real are now real, and perhaps we haven't paid enough attention to sci-fi to understand things like AI and the role of morality or ethics in how AI does things, the role of questions in genetic engineering. So to me, this is what I think I love sort of at a meta level about sci-fi, that it poses questions and makes us think about things which, even if they aren't real yet, will be real someday. Yeah, so what as that? But as a more concrete answer to your question about what about sci-fi that I really like, there are a few stories that stick with me. One which explored this idea that in the future people forget how to do math because computers take over and essentially do all the math. And then at some point, somebody rediscovers that you could do some of this sort of math by hand, and what the consequences of that are. So in any case, the point here is maybe bigger than just about math. It's about how knowledge is really subject to fashions, And what are interesting questions now are different from what were interesting questions 100 years ago, and might be very different from what are interesting questions 100 years hence. And so we've forgotten things like elliptic functions or things, except for a few people that care about it. Sort of what were general kind of knowledge among maths college students in the 1930s is very different from what is math knowledge now, and I'm sure that's the same with other disciplines as well. So this idea in science fiction about absolutes and transient phenomena and how they shape sort of what is happening, I think that's something that I really like.
Thank you so much. Our next question comes from Scott, who asks, can you please talk about the field of geometry in general? What are cutting-edge topics that mathematicians are exploring in the field, and why?
There's geometry in general is about, so one view, and that's maybe close to how I think about it, is about transformations of objects subject to certain rules and what can we say in generality about these transformations. So in that sense, it's not tied to one particular model or one particular phenomenon, but it's more about what can we understand about general classes of objects. And within geometry, there's lots of things that are happening now. So there's work on a program to classify all manifolds of a certain dimension. So for example, this is well known for a while now, that if you take closed surfaces and that are orientable, so that's a technical condition, they essentially are, you can list them out. There's a sphere, there's a donut, and then there are kinds of surfaces that you get by having donuts attached to each other. So surfaces with multiple holes. And it's completely classified by the number of holes. Now, can we do this with three-dimensional surfaces? And a lot of progress has happened on this recently. There's work by Perlman and other people that have essentially solved this. Can we understand or make a list of all possible three-dimensional geometry? And so there's questions of that type. There's also questions about other kinds of geometry. So there's geometry called conformal geometry, which has to do with transformations that don't preserve necessarily lengths, but preserve angles. And this turns out to be relevant to a whole host of questions, including the structure of our visual cortex. It turns out that the mapping between what we see in the back of our retina and what our brain kind of sees in the cortex is a conformal map. And so understanding this conformal map has something to do with how our brain makes sense of what it is that we are seeing. This question also turns out to be relevant to practical problems with surface morphing. And so there's a lot of recent work on what one might call active materials. So these are materials where you change some stimulus, you shine light on it or you heat it, it undergoes a prescribed kind of transformation. And that's at the level of local things. And then a question is, you put a bunch of these together into some global object, how does the object transform? And there again, these questions about geometry and transformations. So this is on the applied end of the spectrum, are very, very relevant. So people are trying to use conformal geometry to understand what you can do with pneumatic elastomers and how can you make objects that transform in prescribed ways. So geometry right now, I think it's a very active and fruitful area. There are questions that people are looking at in connection with, say, relativity and space-time. What's the geometry of the universe, and what can we say about geometric equations that we write down. Are these things stable? So sort of questions that are borderline philosophical, but might have practical consequences in how it is that we view the nature of the universe. There's also questions from geometry on sort of in physics from very field theoretic perspectives, so high energy physics and what kinds of particles are there and how do they interact. All of these also turn out to be related to some kind of geometric questions as well. It's hard to give sort of a simple answer about just because it's so broad, and there's activity in all kinds of things.
Thank you very much. Our next question is from Alita, who asks, what first inspired you to do research in this particular field?
So it started, I think, with the problem of crumpling. I know most of you know Waktang, a good friend of mine. We actually shared an office when we were postdocs, and when I was starting on this work, we were both at the University of Chicago, and one of my collaborators from there, Tom Witten, asked me this problem. We were just chatting, and he said, why does paper crumple? And I was like, what kind of question is that? Of course, paper crumples. And then he pointed out that yes, it does, but it's not completely trivial, and there's something here to think about. And I think something that stuck with me from then was that things that we take for granted, that flowers are ruffled, or lettuce is ruffled, or these things are actually worth examining, because yes, it's true that we see this so often that we take this for granted, but sort of why? And so both in terms of the actual content, the connection of elasticity with shapes, as well as the philosophical idea that we should examine things that are around us. So one of the questions that they worked on, and perhaps Vakhtang thought about this as well, is why does, when coffee dries out, it leaves a ring, it leaves a stain? And this was a big question then. And of course, you might be like, why? Of course, coffee leaves a ring when it dries out. What is the question here? The point was that there are some interesting fluid flows and mechanisms by which stuff which was in a drop initially gets pulled out towards the edge. So, that has applications, but also it's interesting to think about it. So questions of this type, that you see phenomena around you, but you're able to step back and ask why such a thing is. Yeah, so that's something stuck with me as a philosophy. And in terms of the actual details, that's where I first got interested in this connection between elasticity and geometry. And then after working on sort of the flat problem where you get these folds, I started thinking about where else do you get elasticity and geometry, and then I started thinking about these hyperbolic things.
Thank you so much for the great answer. We have another question from Scott. Scott says, I believe I heard you say in some form that natural things grow and develop their shapes based on the efficient use of their available energy. Is there anything you've observed in nature that has really amazed you in terms of efficiency or form?
That's a great question. So, I mean, yes, there's several things in nature that amaze me, including, how our cells are organized, that they have all these, how nature has learned to exploit everything it can, chemistry, physics, mechanics, to make something as complex as us. But in terms of the energy budget, that maybe I took things a little bit too far, because what nature optimizes for is often a lot fuzzier than something that we might do in engineering, as to, you want to send a rocket to the moon, you want to optimize the energy that it takes to do it. But nature often does not have a single objective. It's trying to do many things well. And but yes, the fact that things organize themselves, self-organize, we grow from a single cell that doesn't know geometry, doesn't know up from down, into something where our eyes are different from our fingers, are different from our bones, and how all of this, that's a fascinating problem. And I know lots of very, very clever people are thinking about various aspects of it. And I don't think anyone even can begin to grasp sort of the totality of such a thing. And that to me is really fascinating and not anything that I'm expecting will be resolved not by me, but not in maybe 1,000 years. I mean, not by me, not in my time, but not maybe in 1,000 years.
Thank you so much. We have a question from Brian who asks, how might quantum superposition give rise to the natural geometric patterns we observe in the physical world?
That's a great question. So there's this aphorism, I heard it from somebody, do I need to know quantum mechanics to understand my table is sitting together? And in a way, the answer is yes. But in a way, I think the answer is also no, in that this reductionist approach of trying to break everything down to its very elementary parts and putting this back together, it's certainly true in principle, but it's very hard to carry out in practice. So it is true that quantum superposition, and in fact, there are probably even more philosophical questions about what does quantum superposition mean, and what is it that we are observing, and so on, which I won't get into. These are interesting questions, but from a standpoint of trying to make a car or, something, or mixing coffee in your cup, we work often with different models at different scales and not worry so much about how a model at a smaller scale translates to give you a model at a larger scale. So what I guess I'm trying to say is I don't see myself a direct way of going from things like quantum mechanics to things that we see the transformations in the geometry around us. And in a way, this may be a little bit dissatisfying, but I'm okay saying that I'm going to look at this phenomena and make a model or some understanding at this scale, which should be based on something more fundamental, but I don't know how to make that transition.
Thank you very much. We have another question from Syed. What is your most memorable or eureka moment for you from working in the field?
So the one eureka moment that I actually remember very clearly is the following. So I said that we could do this surgery where you introduce these things hierarchically. Quite early on, we figured out how to introduce one such point, one point of surgery. But these things are nonlinear equations and they interact with each other. And so it wasn't clear that it was even possible to have more than one such point. And so there was one day I was, talking with my student in my office, and I quite clearly remember we were working on the board, and then all of a sudden it occurred to us that we were looking at straight lines, which are geodesics, where really for the nonlinear PDE, we should be looking at characteristic curves which might be straight but don't have to be straight. And that's a simple idea in hindsight. We should have thought of this years prior to that, but it took us, I could say, a couple of years to get this one insight that we should look at characteristic curves instead of geodesics, and that completely opened up the problem to us. So that was one such moment.
Thank you very much for your answer. We have another question from Alida. Do you have any thoughts on how this research may influence the future of sustainable material design?
That's a very interesting and important question. And to the extent that one can work with soft and, as far as possible, natural or naturally recycled materials, that will help in making sustainable material design. But beyond that sort of aspirational thing, I'm not really a chemist or a material scientist, so I cannot speak to how it is that people might build an actual platform or a material that implements some of these ideas we see in the math. So I do talk to people that work with elastomers and other kinds of liquid crystals, so I'm somewhat familiar with what they do. And that's very different from metallurgy or these processes that do take a lot to extract usable products from natural things. But still, it's not clear. At the moment, I would say even it's not completely clear what we can get out of the math before we can have something concrete to say to an applied person that will go ahead and maybe build some of these things.
Thank you so much. That is all the questions that we have for today. Thank you for joining us, Professor Venkataramani. We really appreciate you taking the time to share your research with us. And thank you everyone for joining us online. If you liked this lecture, we also have other lectures available on ATCO's YouTube channel to watch. And our next speaker series event is going to be on May 14th. With that, I'll send you off to enjoy the rest of your day, and we hope to see you next time. Thanks so much.
Thank you all. Thank you so much.